Gotta look, good for the stream.
Oh, why didn't I do that?
You're looking sharp, man.
Yeah.
Looking sharp.
All right, is it live?
Yeah. Is it?
All right. Yeah, it should be. All right. Class starting in
3,
2,
1,
go. Blast off.
All right. Hey, today we're gonna be doing Wilson's theorem. Yeah, Wilson's theorem. This is what our objective is, to prove this theorem today. What do we remember from Fermat's little theorem? That was a pretty challenging proof relative to our other stuff. So, any thoughts?
It's best used in the context of contradiction proofs, but it can be used with any method of proof, really.
Sure. Yeah.
Just something to add.
Anything? Any more insight?
Hang on a second. I don't think that was a.
Oh, we already have Wilson's theorem
We
calculated.
talked a lot about residuals, correct?
Oh,
Residual
yeah.
sets.
Oh, yeah.
We discussed
I
residual.
remember.
Yes, we did discuss residual sets.
But residual sets are more formally defined in the basis of something called inverses, modular inverses. Okay. So before we cover Wilson's theorem, which I should write it states. You should write this down if you don't have it already, but I think some of you do from last time. It's p minus 1 factorial is congruent to -1 modulo p. Okay. And that's not the theorem, that's just what it is. So it says that if and only if p is prime, then this. So if p is prime, then p minus 1 factorial is going to be congruent to -1 modulo p. Okay? Before we cover that, let's talk about inverses. So it's not a lemma, but a tangent in the lecture that we'll circle back to our Wilson's theorem proof is inverses. I'm gonna try to focus on my penmanship in this class. Hopefully it's not as bad as it usually is. All right, inverses. What are inverses in modulo? Okay, inverses are a number b relating to a such that a times this number b, this inverse, is congruent to 1 mod n. Okay, so it's a number that when you multiply to a, you'll get 1 mod n. Okay, let's look at some examples. Okay, so let's say you're in mod 13, or let's do 11.
Does A have to be an integer?
A does have to be an integer. Okay. Yeah. Okay. Let's do mod 11. Okay.
Would you like to clarify in writing that?
Yeah. So let's let A equal 4. Okay. What can we multiply to 4 to get 1 mod 11? Remember, mod is such that AB minus 1 is going to be divisible by n. So, yeah, not 8. 3, good, yeah. Why? Because 4 times 3 is equal to 12, which is 1 mod 11.
Charya, just wanted to clarify, I was thinking of addition. That was just a brain fart. I swear to God, I'm not stupid.
You're good, dude. You're good.
You're okay. It's okay. So the salutation.
Thank you.
I always write slanted. I need to lock in.
I do that too. I don't know how to fix that.
Oh, yeah, sorry.
Use the
Dotted
face
board, writing slanted.
Oh, just right straight.
Yeah, that's one, bro.
Thank you.
All right, and we decided that inverse, that question mark is 3. So 3 is the inverse of 4 modulo n, or mod 11. Now notice, does a number have to have only one inverse? No, because again, mod is a cyclic operation. Think about clocks. Clocks are in mod 12, okay? Goes around multiple times, but eventually all the numbers are going to be in mod 12, right? Like no matter how many times it circles. So what's another inverse of 4 in mod 11?
I think. Was 14? Was 14 the inverse? I just want to throw it out there.
14 inverse. I don't
Yeah,
know.
it would.
it's-
No, it would. Never mind.
So you plug in 14 and you're gonna.
Oh, wait, no, it would be, right? Because then it'd be 56.
23 over 4.
56, which is one more than 55.
I was 23.
Yeah, 14. Yeah,
14, because 14 times 4 is what?
56.
56 minus 1. Yeah, 14
What was
works.
trying to tell me I was wrong?
So
Wait,
14
I
is
don't get
another
it. Wait,
inverse.
how's 14?
Does
What is 14 times 4?
E doesn't have to be an integer, right? Just A.
6?
Yes. And what is
Like-
56?
No, they both have to be integers.
Both have to be integers.
Yeah, everything right now, number 3 is going to revolve around integers.
Okay.
So you just keep adding 11? So would
Yeah,
negative 8 also be?
Exactly. That's a key point, which is you add 11 each time. Why do you do that? Why do you add 11 each time? The answer lies in what do you do in a lot of these modular arithmetic problems? You reduce them, right? For example, if I'm trying to dictate, okay, what is 9 times 8 times whatever, 5 mod 5? What can I do? Okay, I know 5 is what mod? What is it going to be?
That's going to be 0.
0. So I know that the whole thing is just going to be divisible by 0 by 5. What about 9 times 8 times 6? I can rewrite each of these individual numbers as the reduced mod form to make the operation easier. Yeah.
So wait, is it like, because you want to add 0 to both sides because you want one to still be like.
So you add 11 to
one,
both
And
sides.
then you want the other side can be, it has to be 0 mod 11, so it could be anything that's divisible by 11. So like if you added 33 would count.
Divisible by 11. You're close. You're like, you know what? The English teacher's like, yeah, you're right there. You're right there. You're right there. Alright, I'll circle back to that. You are adding 11 each time, and in a sense, it is divisible by 11, but not the number itself. It's divisible by 11 plus a number, which you guys, I'll explain. But basically, what do we do if I'm trying to see what is this mod 5? What is the remainder of this? Well, I can write 9 as what mod 5? 4. I can write 8 as what? 3. And I can write 6 as what? 1. So this is equivalent to 12 mod 5, okay? What can we write 12 as mod 5?
2.
Oh, yeah, 2.
2, right?
One include.
So notice how we just kept reducing? That's because 9 is congruent to 4 mod 5. That's because 8 is congruent to what? 3 mod 5. And so on.
So 2 is congruent to what mod 5?
Just 2.
Just 2 mod 5?
Yeah.
Okay.
Also, -3.
Yes.
Can have negatives, but don't get too confused. Stay over here right now. The point of the matter is you're doing a lot of reducing, right? You have multiple inverses, but like Kathir said, you're adding 11 each time. It's almost as if that part is divisible by 11. Do we get that 3 is the smallest positive integer? That's an inverse of 4 mod 11. This is the smallest, right?
Yeah.
There's nothing else? What's the next one? 3, and then there's what?
14.
14,
25.
25, and so on.
3.
Now I want you to write, what is 25 mod 11? What is 25 congruent to in mod 11? Start reducing.
11, 3.
It's 3. What is 14 congruent to in mod 11? 3. What will 36 be congruent to mod 11?
3.
3. All of these bigger inverses, because you're just adding 11 each time, okay, so you have this number 3, right? And
adding
you're-
11 in mod 11.
You're adding 11 each time. It's almost like you're doing 3 plus 11k. Now, when you take this mod 11, obviously this is going to reduce out and you're left with 3 each time.
Wait, I
So-
don't get how this makes me wrong though.
Is
I was just saying you take that smallest one, you can add anything that's divisible by 11 to
You weren't wrong. I don't think you were wording it. Maybe I didn't understand.
To elucidate, you're stating that each number in this set, each element within this set will always be congruent to 3 mod 11. or is there an
Exactly,
exception?
exactly.
I've been studying the SAT vocab list.
Who, me?
Yeah. Elucidate.
Okay.
I don't even know where we find it.
So are we clear on inverses? Are we clear on inverses?
That's
Yeah, yeah.
What? This is laser beam.
Laser dim.
Oh,
Yeah.
I haven't listened to it.
Would you like to attempt to prove?
Now let's talk about one last thing before we get to our proof. This is a really critical thing, guys. Okay. When we're dealing with numbers in mod, they can always be reduced to something that is less than the mod itself. Let me explain. Let me go. Let's say there's a mod n. Okay. If you have an integer a, okay, and you're trying to see what is it congruent to in mod n, it will always, and let's say a is greater than n. Let a be greater than n. A can always be written as a number less than n itself in what's it called? In mod n. Why is that? Because it's the same thing with division. For example, when you're taking the remainder in division, right? You have, let's say you have 10 divided by 3. You can write this as 3 remainder 1. The whole point of the remainder is that it does not exceed 3. Otherwise, you could put another 3 in, right? If this was 3 remainder 4, then I could put another 3. If it was 3 remainder 5, I could put another whatever. You know, you get. Does everybody get what I'm saying?
Indeed.
So just like that same remainder concept, you can always write a. If a is greater than n, you can always write it as an integer that is less than n itself. For example, in mod 5, write 8 as what? You can write it as 3.
Wait, does every number have an inverse? Every integer?
Every integer has an inverse. And I'll show that with actually a throwback. It's low-key gonna be pretty sick.
More complex data be displayed
Huh?
with a three-dimensional frequency table.
Does every number have infinite inverses?
I mean, yeah, right? Because I can just add 3 plus, or like, there, for example,
If you just keep adding 11 there.
let's go back to this, right? 3 plus 11k, and k is in the domain of all
Inverse values right there.
real numbers.
No, I literally hadn't.
Why is this so important? Let's look at all the numbers in mod 5. Let's look at all numbers. Okay.
Hurry up.
All numbers in mod 5. Okay. Let's have 1, 2, 3, 4, 5, 6, 7,
Oh,
8,
Is this in mod 5?
9, 10, yeah. 11, 12, 13. Let's look at all these mod 5. This is coming to what mod 5? 1, 2, 3, 4, 0. This is coming to what? 1, 2, 3, 4, 0. It will continue on that forever, of course, logically, right? Like same remainder thing. These are all going to be congruent to this in mod 5. So the residual for any number, no matter how big it is, will always be within 1 and 4. It will always be within, I repeat, it will always be within 1 and n minus 1 in mod n. Right?
Not 0?
A number in mod n.
Okay.
If you have a number in mod n, that can be written as a residual from 1 to n minus 1. It can never exceed that. Okay?
is residual just the same thing as remainder?
Yeah.
Yes.
So wait, why are you making fun of me, Rishik?
Is everybody concrete on this? I need to this is the most important part of the proof.
Yes.
Okay? Is that you could always write any number, no matter what number, as mod an integer between these. It can be
Yes.
1, it could be 1 mod 5, it could be 2 mod 5, 3 mod 5, 4 mod 5.
Wait, 1 on 0.
Huh?
1 on 0.
Because that's not a residual. It's not a remainder.
I get it.
And if it's 5, let's say it's 5. If it's 5, if the remainder is 5, what is that? That's just 0.
Yeah.
Because you can just put another 5 in there.
Yeah.
Just like in division. If it's, so 5, this is 0. So 0 and 5, we don't need that. If it's 6, what can be written? It's 1. If it's 7, it's 2. If it's 8, it's 3. You notice how you never need to go past n minus 1. It can always be written like that. Good? So you can have a number, whatever. I don't know, some crazy big number, 1.378 times 10 to the whatever, 85th. In mod 5, it's gonna be either 1, 2, 3, 4, or 5.
Wouldn't that be 0?
That'd be 0. Whatever, if it's had 85 digits, whatever it was, it'd be 1, 2, 3, 4, 4. Mod 5. Is everybody clear on that?
Yes.
Yeah.
Of course. I'm gonna go through a simple iteration of Wilson's theorem, and then I'm gonna prove everything. Everything was assumed, so there's no gap in logic.
Oh!
Yo, that's how you want me. Just let me prove it.
Oh!
That's short as bar, bro.
When are we releasing that song?
Never, bro.
Sherry, could you please say
Staying on
prove
my
it again?
band lab forever.
Sherry, can you please say prove it again?
Prove it?
Prove it. Okay.
Okay.
Why aren't you pirating?
I did let you pirate.
I didn't have enough time.
Why are we discussing piracy?
Because
Alright, I guess this first iteration of the proof isn't a really proof, it's just an example that's gonna be pretty eye-opening, I hope.
It's
Okay.
just an instance of Wilson's theorem in some computation.
Sure, yeah. Let P equal 7. Let P prime equal 7. Okay? You're trying to show that 6 factorial is gonna be congruent to -1 mod 7. Okay? What you can do with this is say, okay, 1 times 2 times 3 times 4 times 5 times 6 is congruent to what, right? And let's list these numbers down.
What are you doing? Is something wrong with you?
So much glare. It's okay, that's good. Okay. 1, 2, 3, 4, 5, and 6. You multiply these together. Let's ignore these for just 1 second. Right? Because is multiply something by 1 gonna have any effect on its mod? No. So we can almost like erase this entirely. Okay. But what about this? We're trying to get inverse duos, okay? Right? Look what happens. What's 2 times 8? 2 times 4. 8. What is that mod 7?
That's 1.
That's to 1. What's 3 times 5?
I want to say 15.
15, which is congruent to what mod 7? 1. Huh.
It's 2 and 3.
2 and 4 are inverses, and 3 and 5 are inverses.
So,
So when you multiply all these together, it's going to be, okay, so you have the 1, and you have the 6. You have this times this, which is going to equal 1 in mod. And this times this, which is going to equal 1, so times 1. And then times 6. Okay? Now, what is P minus 1 mod? What is P minus 1 mod P? Think about negative numbers.
-1.
-1.
Oh.
So we could write 6 as what?
Wait, but this is always work?
-1 mod 7.
We could write 6 as -1 mod 7. So 1 times 1 times -1 is congruent to what? That's -1 mod 7. So it works for that. The goal of this example is to show you in a real case where the inverses, we're always trying to look for the inverses, right? The inverses are always gonna be in this set.
Wait, and this works because the inverses can always be simplified between 1 and 1 less than the mod n.
You will always find an inverse of a number within this group. Why is that?
Because
Let's say you want to find the inverse of 5.
Yeah.
Okay. Okay. You want to find the inverse of 5 in mod 7. What do you do?
You go. Oh, I probably multiply by 3.
Sure. You multiply by 3. How do I explain this?
Yeah.
Oh, okay.
You just multiply 5 by any number bigger than 1. And
You want to find something where 5 times a number is gonna be something is gonna be equal to 1 mod 7. Right? Does that number ever have to exceed 7? No. Why? Because we just showed that all of those numbers can be written from 1 to n minus 1, and n minus 1 is 6. So you have everything you need in this set. I'm trying to show you that you can always find an inverse in this set. Okay? Now for the actual proof. It's going to be a rigorous proof. Now I'm going to reiterate what I just said at the end of this. Okay. How can we write p minus 1 factorial? 1 times 2 times all the way down to what? P minus 2 times p minus 1. We'll have that up there. Okay. We talked a lot about inverses, so we're going to focus a lot on inverses in this proof. I've talked to you about inverses, and I've just told you there's always going to be an inverse. I've never proved it. Like Kathir said, how do we know? Like Kathir asked, how do we know if there's always an inverse? Okay. An invert. What do we start with proofs always? Formal what? Definitions. Okay. What is the definition of an inverse? Let B be the inverse of A. Then what? A times B equals 1 mod. Say P. Okay.
Separate value.
Are you good with that?
Of course.
Okay. From here, what can we do? We could say AB minus 1 is congruent to what? 0 mod P. When something is congruent to 0 mod something. I repeat, when something is equal to 0 mod something, what does that mean? It's divisible
By P.
by P. In other words, P divides what?
Yeah, I think that's what I think. Yeah, that's right.
P divides AB minus 1. Okay. Is everybody okay with this?
Of course.
Yeah.
Okay. When something divides something, let's go back to day 1. What is that? What can we write this as in equation form? P times what? There exists an integer what?
K.
K. Such that P times K is equal to what?
AB.
AB minus 1. Now this part is super genius. I think it's so brilliant. Because it refers back to something that we learned a long time ago. Okay?
Just is the K written as an
That's why I
exponential
add 1 to both sides and subtract PK. In other words, I wanna get the 1 alone. Jack, I don't care for the little things.
No, I'm just clarifying. Do I write this down as p to the power of k or just p times k?
P times K.
But,
Just wanted to clarify.
but,
Alright. Okay,
Three-dimensional frequency tables we use.
so we want to get one of, hey, okay. Just bear with me for like a few more minutes. Okay, 1 is going to be equal to what? What can we write this as? Basic algebra.
negative p k minus ab.
What?
AB minus PK.
That is what it is.
No, it's AB minus BK.
You just threw a negative.